Yeah, fine. Do you have any doubts still right now? Yeah, if you have, you can just type it out and I will try to resolve it. Okay, fine. Okay, now let's continue from here. And associative law is like when two statements are given. See here, we have to take in mind that here in each of the statement, the conjunction or disjunction is same. Okay, here if p or q or r is only given in this associative law, as you can see, q or r and p or q is interchangeable. Okay, it doesn't, I mean, these both are equivalent. Even if you do one before another, it will give the same result. Okay, in commutative law, p or q will be equivalent to q or p. It won't affect, I mean, the changing of the order in this will not affect. It applies for both or and. Okay, and here distributive law, it is different from associative law because in associative law it is only or. Okay, in both of the thing it is only or it is and. But here in distributive law, if p or q and r is present, we have to distribute that p over q and r. Okay, as you can see here, mm, this p is distributed over q and r. As you can see here, p or q and q p or r. This r is distributed to both q and r. Okay, yeah. So this gets distributed. This p gets distributed to both q and r. So that is p or q and q or r because that and is already present inside. Okay, so let's take for the other case. Okay, and here p and q or r is distributed as p and q or q p and r. Okay, here absorption law is given. Okay, in this absorption law, as you can see, p or p and q is given, then p absorbs this whole statement. Okay, so it only gives p as the answer. But here, and it is the obvious say opposite. Okay, as you can see, if we distribute it, p or p and p or q is given, right? So here, so it will give p and p or q as a result. So it's either p and p or p or q. So either way, we'll just consider this p and p. So it will just so this p. So sorry, it's p or q, right? So it will give p or q. So p will dominate over that q. So therefore, it will be only p at the end. So this is absorption law, and it goes the same different for the next statement. So if p and p or q, okay, as you can see the difference of or and or and here. It's confusing. I mean the words. Okay, here p and p or q is present, right? So you can see the difference between or and. So here it again the p absorbs the p or q, so the p only remains. Okay. De Morgan's law, as I already explained, what how negation acts on uh, does the compound statement. As you can see, negate the both the terms inside and change the sign inside. So that is De Morgan's law. As you can see here, negate P, negate Q, and the R becomes and. In the second statement, negate P, negate Q, and the and becomes R. Okay, so that's the difference. So implication law is that is P, then Q is not P or Q. Okay. So here, let's take an example. Okay. I'll just explain this example because we are in a revision. Okay, so I'll just explain this example and go to the next topic. Okay, so here we have to show that uh, both these statements are equivalent. We have to transform one of the statement to other to prove that both of these statements are equal. We can prove it with the truth table, but here they have asked not to use it. Okay, so we have to transform it. Okay, so first we are taking this big statement, the first statement, and we are applying the De Morgan's law here. Okay, so if we apply the De Morgan's law, as you can see in both the statements. Okay, so here the double negation law applies in this statement, and we distribute the not p over the p or not key. Okay, so as you can see, this statement becomes false, and now just this remains. Okay, just not p or not q, which is the original statement that we want. We just have to expand this. Okay, that's what it means. We have to expand one statement from another, and we have to reduce it. As you can see, we apply De Morgan's law first, and then we reduce this statement. I mean, as you can see here, this into false because it gives only false whenever, whenever the p and or p and not p is conjuncted. Okay, so like this we can show it. Okay, so this is one in such an example, but right now I'm just taking this example. Okay, like this we have to prove other so this is just basically just proving from one statement to another. Okay, now let's see about normal forms. So it is the standard way of representing compound proposition. Okay, a standard way means it includes every variable that is present. Okay, okay, before that we need to know what is an elementary product is. So that is the product of variables and their negation in which each variable is present at most once. Okay, so that is basically the universal set contains the variable and their negation and making product out of them. Okay, so if p and q are present, then not p and not q also present, and we try every possible combination out of it. Okay, so as you can see here, p and q, not p and not q, not p and q, p and not q. Okay, so these are the uh, elementary product, and each of the individual is also treated as elementary product. I mean the p, not p, q and not q is also treated as. Okay, and d and f. So disjunctive normal form is something, a compound proposition which is sum of these elementary product. As we have seen already, the elementary products are these, that is it only has I mean conjunction, that is and. Okay, using this and we are adding those statements, that is the statement which has that and. Okay, so which is disjunctive normal form. Here disjunctive means or, right? We are using or statement to connect different elementary product. Okay, as you can see in this example, p or not p and q or not p and not q. Here, as you can see, there are three different terms. Here p, not p and q, not p and not q. Here these three are elementary products, right? Because they use and there. Okay, we are just adding these three using or, right? We are using or here and here. So basically this means that it is we are disjuncting those what we say that elementary products. Okay, so it is disjunctive normal form we say. Okay, and Min terms is just the elementary product in which each variable or its negation occurs exactly once, but not both. Okay, the min terms will have all the variable. As you can see, the min example is p and and not and q, p and not q, not p and q, not p and not q. Okay, which is the elementary product in which each variable occurs exactly once. It is not at most once, it is exactly once because both the variables must be present. That is min term. Okay, it is not at most, it is exactly once, not more than once or not less than once. It is exactly once. Okay, so principal disjunctive normal form is representing uh, it is we are using the min terms to disjunct. Okay, here as you can see the three terms are present there. Okay, p and q, not p and not q, p and not q. Here these three are min terms, right? Because it has exactly once. The each of the variables are exactly once there. Okay, so and we are oring. We are using the or to disjunct all these terms. So it is basically we are using min terms. Okay, in principal disjunctive normal form, that is PDNF, we are using only min terms, not the elementary, just the elementary products. Okay, so any compound forms can be expressed as PDNF or PCNF. Here PCNF is just principal conjective normal. Okay, it is principal conjective normal form is the exact mirror of PDNF. Okay, guys. Yeah. Here, yeah. Let's see about elementary sum. It is the same of the elementary product, but the thing is, has or instead of and. Okay. The conjective normal form is that we are using those elementary sum as a product. Okay, a compound CNF is conjective normal form is a compound proposition which is product of elementary sum. That is, it has and in between those elementary sum. Okay, so max term is just the opposite of min term. Okay, that is it exactly has one variable of each, but not both. But it has or instead of and. In min terms we have and, in max terms we have or. Okay, so PCNF is the principal conjective normal form. That is, we use max term and use and to conjunct it. Okay, so that is PCNF. Okay, so here we have to find the disjunctive normal form of this statement. Okay, here as we P then Q or P and Q. Here P or Q is there, and we are just uh, expanding this P then Q. If P then Q is expanded, it is not P or Q, and not P is an element and Q is an element, and then P and Q is an elementary product, right? So these three are considered as elementary product, and or is used to conjunct all these. So it is a DNF, that is disjunctive normal form. So construction of PDNF is first we have to obtain a DNF. Okay, like this we have to separate each and have or in between those elements. Okay, and if a variable is missing, then we have to, in the product, introduce it by taking conjunction with T and use negation law. Use distributive law to get the PDNF. Okay, let's see about, the second statement might be confusing, but let's see about it in the upcoming example. Okay, so as you can see here, in this example, P not Q or P and Q is given. Okay. First we are getting the DNF, that is disjunctive normal form. Okay. After that, we must have an and inside, right? Because it is DNF, that is elementary product is the term here. Okay. So we have to have an and. Okay. But the statement must remain true, right? As you can see, the not P must remain true. So we are anding we are using the and with a true statement. Okay, and here the q must be preserved, but it must have the operation of and, so we are anding the q with and we don't have to bother about this because it is already a midterm. Okay, so here to introduce that new variable, we have to use we have to put q or not q. Yeah, because that statement will always give true, right? Q or not q. So we are, instead of using t, we are just substituting it with q or not q. And in this second statement, we are using q, or to introduce that p, we are using p or not p, because p or not p will always give true, right? So right now, after introducing these, we are just distributing it over. Okay, we are just oh, wait, yeah, we are just distributing it over. As you can see, this not p is distributed over here, and this q is distributed here in this statement. Okay, so we'll get four new thing and the remaining one. Uh, yeah, as you can see, this statement and this statement is both the same. So we put it as one statement, and this statement and this statement is same, and we put it once and this statement here. So that's all. So this is what the I mean, principal disjunctive normal form is about. Okay. So we have to do the exact same for finding the CNF. Okay. I mean, we just have to find the CNF, and then if a variable is missing, we have to introduce uh, and use negation, introduce something new and use negation law. Okay. Okay. Something interesting here. Okay. To find PCNF from PDNF, the steps is just collect all the missing minterms. Okay. If we have the will have some missing minterms, right? We have to put that, and PCNF is the negation of sum of missing minterms. So we have to just negate the terms sum of those missing minterms. Okay. So that will give the PCNF from the PDNF. Okay. Mind it that it is sum. We have to take the negation of sum of missing terms. Okay. Negation of sum of. Okay. Sum of missing terms. Okay. And it's the same opposite. Okay. And PDNF is the negation of product of product. Here PDNF, it is negation of product of missing max terms. Okay. It is the opposite. Okay. So in this example, once you find the PCNF, you can literally follow the above step so that you can find the PDNF. If you find the PCNF first, I mean, the PDNF finding is actually easy. So find the PDNF first and then follow the above step. That is, after finding the PDNF, you have to negate the sum of missing in terms of that PDNF. Okay. So from that, you can find the PCNF. Okay, I'm skipping this example for the next topic. Okay. So now let's take the dual of a compound function. Here we just have the question might be asked, find the dual of it. Okay. Here we have to just replace on and with or with or, and true by false and false by true. We just have to exchange the, I mean, we have to just replace it with the opposite of it. Okay. Then it is a main theorem. Okay. If two statements are equivalent, if both gives the same answer, then their duals are also equal. Okay, it is a theorem. Okay, we just have to keep in mind of it. Okay, here there's an example of finding P or Q not, I mean, then R is equivalent to P or R and Q or P then R and Q then R. Okay, so we just have to find, uh, we just have to show that are equivalent by using the duals. Okay, so we just first expand the P or, I mean, P or Q then R. Okay, as you can see, this is the statement that we get from it, and we just take the dual. That is, we just change the or with and with or with and. Okay, uh, as you can see, we are taking the RHS there. Okay, in this RHS, we are just expanding again, and we are changing the and with or with and. So as you can see, the both of the duals are same, right? So we can imply that these both statements are equivalent, as that both of the dual are equal. Okay, so that's how you prove it. Okay, now let's come to the rules of inference. Okay, okay. Here in rules of inference, first we'll take a note of something is that it is always true. I mean, okay, all premises are always true. Okay, here let P1, P2 till Pn be the set of proposition called premises. Here each of the proposition, that is the statement, is called a premise, and C be the conclusion, the final statement that we get from the premise. If we uh, use those premises, we can get to us end, that is called as conclusion. Okay, we further see about it. Okay, this set of premises together with the conclusion is called an argument. Okay, an argument, that is in argument we try to find some conclusion, right? That's why we argue. So using this premise, we'll get a conclusion, right? So this whole process is called as an argument. Okay, an argument is valid if and only if truth of conjunction of all the premise implies truth of conclusion. Okay, that is, if we take the truth of P1, P2, P3, it must give the conclusion. I mean, the both of it must be same. That is this, and we are, I mean, using of and in all these premises must give the conclusion. Okay, proving this implies that all the arguments are valid. Okay, here the rules are there. We have to follow certain rules to make that argument. Okay, all the statements about line are all the statements about the line are true, so the conclusion is given below the line. Okay, okay, here as you can see there is a line, so we have to assume that the thing above the line is always true, and the conclusion is given below the line. Okay, so here addition law is P or Q is always true if P is true. As you can see, if P is true, if P or Q is given, then P or Q will always be true, right? So if P or Q is given, or P or R is given, P or S is given, it will always be true because P is true. That is addition law. And conjunction law is that if P Q is given, then P and Q will be true. If P is true and Q is true, then P and Q will be true. As you multiply both of these, that is, if you and P and Q, it will always be true, right? So P and Q are true. If P and Q are true, then P and Q, that is the conjunction will be true. Simplification law. If P and Q is given, that is, if the statement P and Q is true, then individually P and individually Q are true, right? Because if the statement P and Q to be true, then P and Q must be true, right? I mean, individually P and Q must be true. So it is simplification law. That is, we are deriving P, I mean individual see, we are I mean the individual P and individual Q is derived from this original P and Q statement. Okay. Okay. So modus ponens. Okay. Here, if P then Q is true and P is true, then Q is true because the modus, I mean the P then Q is given here and we are given that the P is true. Then it will imply that Q is true. Okay. That is called modus ponens. In modus tollens, if P then Q is given true and not Q is true, that is not Q is present, then we get the conclusion that not P is true. Okay, that is in P, P then Q is true and not Q is true, then not P is true. Okay, as you can see, P then Q is essentially what? Not P or Q. But here we are given that not Q is true. Then obviously to make the P then Q true, the no, P must be negated. So that is not, I mean, one of the statement must be true. But here the Q is false because not Q is true. So the not P must be true. Okay, so that's what we infer from this modest tolerance. Okay. Here we first have disjunctive syllogism. Disjunctive syllogism is that if P or Q is given true and not P is true, then obviously Q will be true, right? Because to make that statement true, either one of them has to be true. But the thing is, not P is true, then P is false, right? So that obviously paves the way for the Q to be true. Okay, guys, 1 second, please. Can you see the PDF again? Yeah, fine then. Okay, start from where I left. Okay, so this is what disjunctive syllogism is. So if not P is given and not P or Q is given, then it implies that Q is true. Okay, hypothetical syllogism is that if P, it's like the, how can we say? If P then Q, Q then R, then it implies that P implies R. Okay, it is like a chain. Okay, so if P then Q then Q then R, it implies that P then R. Okay, so resolution is like is something like if P or Q is given, then not P or R is present, then Q or R is true. Okay, so as you can see, P or Q and not P of R to be true. If both have to be true, we have to discard the thing of P. Okay, so that Q and R will be true. So we can say that Q or R will be true. Okay, so here we have something called rule P and rule T. Okay, here rule P is that any premise can be introduced at any step, and rule T is that any new premise can be derived from the rule P. Okay, let's take an example so that you can get a clarity on it. So here, show that oh, T, okay, it is T. So T and S can be derived from the premise PQ, I mean P then Q, Q then not R, P, R, T and S. Okay, here we are using the first step P then Q, that is rule P, that is already given. Okay, then Q not R is already given, so P not P then not R is derived. Okay, so that is called rule T, hypothetical syllogism. So here we are introducing again R as rule P. So, and then not P is derived because from rule T of using modus tollens on 3 and 4. Okay. So, in rule P, uh, we are introducing the sixth one, that is the P or TNS. Okay. So, from 5 and 6, we can declare that T or S is true from hypothetical syllogism. Okay. So finally, we have derived from these premises that T or S is true. Okay, from these given things. Okay, that is, we have used the laws from the above one to derive the final conclusion. Okay, the final conclusion. Uh, it is the same, I guess. So here R not P or Q must be concluded from the given premises. Okay, as you can see, not M and the first and second step are derived. I mean, given from the premises, and then not P is derived from 1 and 2, and P or Q is rule P, and Q is derived from rule T of 3 and 4, and Q not R is rule P, and that is already present, and we are deriving R from rule T, that is modus ponens of uh, rule 5 and 6. And so, rule T, that is, we are conjuncting both the statement 7, I mean, yeah, 7 and 4. We are just conjuncting because both are true. So, we have finally get to the conclusion of R not P or Q. Yeah, that's about it. So, this is how you have to treat some examples like this, as you can see, show that the premises. We have to take each of the statement here as individual uh, premise. Okay, like if you send an email, then I'll finish writing the program. Here S is given a premise of finish the program. P is giving sending an email, and in the second statement, if you don't send an email and I'll go sleep early, then Q is the premise of going to sleep early, and R will, if I go to sleep early, then I'll wake up refreshed. Then R is a statement of going wake up refreshed. From this 1, 2, 3, 4, we have to lead to the 1, 2, 3. We have to lead to the conclusion of, if I do not finish writing the program, then I wake up feeling refreshed. We have to prove this. Okay, that is, we have to prove that not S then R. Okay, so we have given the premises of not P then Q, Q then R, P then S. These are derived from the original sentences of 1, 2, 3. Okay, here we are just giving, I mean, using this PQRS to represent that each statement. Okay, and from that we derive the three premises that is given above. Okay, and then in conclusion, we have to find the thing, I mean, the given here, if I do not finish that thing. Okay. So we are using both the rule P. Okay. From this one and two, we can use hypothetical syllogism. So we can find that not P, then R. Okay. So, and we are using rule P in the four. And so that, yes, is not, I mean, not S is then not P. Okay. Contrapositive on 4. Okay. I think a step is missed here. As you can see, evenness. Okay, I can explain it to you guys. So if not S is given, then not P will be derived. Okay. If not P is true, then R is. Wait, wait. If no, yeah, that is what. If not S is there, then not P will be true, right? So if we combine both 4 and 5, we can get that not S leads to or. Okay, I mean a step is missing there actually, so we have to do the same here. Here we'll take each and every premises and we'll give each and every statement for each variable. Okay, that is here P is it is sunny, Q is it is colder than yesterday, R is we'll go to swimming, and we are assuming that. And then from each of the premises, so as you can see, it is not sunny this afternoon and it is colder than yesterday. We are just it is not sunny is not of P and it is colder than yesterday. That is, we are ANDing it with Q. Like that, we get all the premises, and we have to conclude that we will be home by sunset. That is T. We have to conclude that T is true. Okay, from all these premises, as you can see, this rule P is given here. That is R to P, not R to S, and then we are implying that not R or P from. I mean, we are using those rules to derive the final conclusion. Okay. Okay, in the CP rule, we just have to find that if it is in the form of R, then S, we just have to find that S is true. Okay, so that means that R then S is true. Okay, because if S is true, then R must be true, right? So we just have to find that S is true. Okay, we just have to follow the previous rules like the smallest forms and use these and derive these premises. And then we just have to conclude that this is true. So if we get that, we can conclude that R, R then S is true. Okay. Again, let's move to the inconsistent premises. Uh, inconsistent premises is that conclusion will come as false if you try either way. Okay. That is inconsistent premises. If it is not true, I mean, even if you add all the premises, it will only lead to false. Okay. So it is inconsistent. In this example, the taking is that as you can see, the final conclusion is false. Okay, it is not true. Then it is said that it is an inconsistent. Here the example of three premises is given, and from that it is we have to conclude, and we have to say that it is inconsistent as you can see. If we get false as the final statement, we can say that it is an inconsistent one. As you can see in these as you see this in these premises, uh, P then Q then R if we assign for the division P then R and S then not R, R then not S, and R then not S if control stable 4, and then P then S this global T. Also, I put a difference then P then not S and after that P and S is reduces the that is that, and from there P for T, that is simplification. Not is rule T, and simplification of this segment. Right. Yeah, if P is 2 and the sixth one, that is P is not is 2, then we must say that P that not is 2, and then not P is not P is also 2 because amount of the modus terms of 6 and 9. So that we finally have both P and not P. So if we try to add it, it will finally give what? False, right? So we can say that it is an inconsistent premise. Even yeah. So if it gives finally as false, then we can say that it is inconsistent. So in the indirect method, so we are using this inconsistency to prove our statement. Okay. In the indirect method, we are just taking the final conclusion and we are negating the final conclusion. Okay. And if we negate and find that it is inconsistent, then the original thing is consistent, right? If we negate the conclusion and find that it is inconsistent, then the original statement is consistent, right? So we are just using that inconsistency to find the original consistent thing. Okay. So that is basically indirect method. So with indirect method, we have to find the, we have to conclude that it is consistent. Okay. Using indirect method, derive, derive P then not S from the given premises. So we have to first negate it. Okay. Now the P then not S must be negated. As you can see, the additional premise in the additional premise, P the not S is given. We are deriving P the not S, that is P and S. We just have to prove that P and S is false. Okay. If we found that P and this whole thing is false, we can say we can say that the original statement is true because the negation. The conclusion's negation is false. Using the conclusion negation is false, so that obviously the original statement will be true. As you can see, P and S is used here for as you can see in the sixth step rule P, and from that S is simplified and it is further used. But at the conclusion, you can see it is F, right? So it is inconsistent. So therefore, the original conclusion is true. Like that, we can find it not using the direct way, but we are just going around. Okay, we are not going in a straight way. We are going around. That's it. And these are some of the examples of proving it. That's it. Okay. Here, proof strategies or techniques. That is direct proof first. Okay. This method is used to prove the statement of the form P then Q, in which we have to prove that Q is true by assuming that P is true. Yeah. It's just the same. We just have to find the truthfulness of the statement. Okay. Square of an odd integer is odd. Okay. We have to find. We have to give the proof for it. Okay. Uh, square of here, square of an odd integer is odd gives if n is an odd integer, then its square is odd. We have to change that statement like that. Okay. If n is an odd integer, that is here, if n is an odd integer is P, then square is odd. Square of n is odd is Q. Okay. We have to change the statement like that. Okay. We have to give proof like assuming n is equal to k plus 1, obviously. If I keep it to k plus 1, it always give what? odd number. Okay, we just have to square that, and after squaring that, we can get the fact that uh, it is 2p plus 1, which is always uh, what odd. Okay, so like that we have to prove with this direct method. uh, like that. In the third example, let's see if m on n of perfect square, then m and then m into n is a perfect square. Okay. So that is if m is equal to a square and n is equal to b square, then m and n is a b over square, and we can aggregate a b to something called c. So obviously, m and n is m into n is a perfect square. As you can see, this third question is itself that in the form of P then Q. M and N are perfect square is P and M into N is a perfect square is Q. So it implies that M and N are perfect square, then M into N is a perfect like that. Okay. Then prove by contrapositive. I mean, we just have to change the position of P and Q and then negate it. It is contrapositive, as I have said earlier. Okay. So here we have to say do the same thing, but the thing is we have to change the places and then we have to negate those stuff. If n is an integer and you are given that n is an integer and 3 n plus 2 is odd, then n is odd. Okay. Here we have to devise that thing which is using if n is even. Okay. Then 3n plus 2 is even. Okay, we have to we have to change the position and negate it. So, as I said, so here n is odd is comes first instead of second, and we are negating it. That is n is even. And 3n plus 2, the first statement is coming second, and we are negating it. 3n plus 2 is even. Okay. So right now we have gotten the contrapositive and we have to move further on it. Okay. Assume n is even, so n is equal to 2k. So prove that 3 into 2k, which is 6k plus 2, we 3k plus 1, 2 into odd is even. So the statement is proved here, as you can see. So therefore, we have proved that statement. Okay, I mean it is true. We are proving using the contrast. I mean, contrapositive. Okay. Here, in this contrapositive method, we just have to, be mindful of that. We just have to change the places and then put negation on both after changing those places, and then go via the direct method. That's it. It's just the revision of what is given the. Okay, so proof can be done using mathematical induction too. So let's see what mathematical induction is. So let P of n be a statement to prove that it is true for all n belongs to the natural number. We have to apply it in mathematical induction. Okay. So we have to first take a base case. Okay. We have to first prove that it is true in the base case itself. Okay. That is equal to 0 or 1. Sometimes it is 0 or sometimes it is 1. And hypothesis, we have found the hypothesis that P of n is true for n is equal to k. that such that that statement is true. We have to assume that P of K is true. Okay. And we have to induct it. So we have to just increment it by one. Okay. So the next statement is also true. We just have to prove that the next statement is also true. Okay. So assume that P of K is true and prove that P of K plus 1, the next statement is also true. Okay. So which leads to the conclusion that P of N is equal to true. Okay. First, we have to find that the initial condition is equal to true, and then we have to assume some K value and some value, it is P of N is true for some value of K, and then we have to prove that the next statement is also true. If we prove that, then we can conclude that the whole statement is true for all values of n. Okay. Here, as you can see, 1 plus 2 square plus 3 square till n square is equal to n into n plus 1 into 2n plus 1 divided by 6. Okay. Here we just have to prove that that is true. Okay. Here, base case is 1. Okay. As you can see, 1 is put for there and 1 into 2 into 3 divided by 6 is 1. So LHS is equal to RHS. So the base case is proved there. And we have to assume that P of K is true. That we have to substitute K instead of N. Okay. As you can see, the statement changes to K into 2K plus 1 into K plus 1 divided by 6. So this is the first step. Then we have to take the induction of it. Okay. Induction of it is K plus 1 in into K plus 1 plus 1 into 2K plus 1 plus 1. Okay. When we expand it, you can see in the RHS, it is K plus 1 into K plus 2 into 2K plus 1 into 3. Okay. If we take both the LHS and RHS, um, so basically, we just in the next step, what will be added in the initial statement? We just have to add another k plus 1 the whole square, right? Basically. So if in the hypothesis we have assumed the p of k is 2, we just have to add that. Rather, in the next thing, it will be k plus 1 the whole square, right? We just have to add that term there. Okay. So in that first statement, we are just adding that k plus 1 square in the thing, okay? And then we are equating it to the RHS. That is the original k plus 1 statement that we have derived right now. From that, we have taken the k plus 1 as common and put forth the other thing. Yeah. And we have proved that after putting that 6k and plus 1 the whole square in the first statement, this both statement gets equated. Then LHS is equal to RHS. So we can conclude that P of N is true for all n greater than. So in the induction set, we must be mindful of that. We have to prove that the base case is true. And then we have to form a hypothesis that P of N is true. And then we just have to induct it. That is, we have to prove that the next statement is also true. K, I mean P of K is true now. Then the P of K plus 1 is also true. We have to prove that. Okay. If we prove both are true, I mean already we assume the first one is true and the second one is true. So it to be true. Then the statement is true. Okay. That's what mathematical induction is about. Guys, right now I have completed unit one. You guys have any questions?
Can you upload
I
these
mean,
notes in the WhatsApp group?
yeah, sure.
Thank you.
You're fine with the explanation, right? Or does somebody have any confusion in the thing that I have explained? Okay, fine then.